Okay, let's look at how the first part of this lab works, the time of flight experiment. Here we are. So what just happened there? Huh? In this part of the lab, we're going to measure the speed of sound by time of flight. That means we'll measure the time it takes for the wave to travel between 2 points with a known distance between the points. Okay? This is a classic experiment, but the way we're going to do it, we'll use some rather nice precision equipment. We'll measure the time it takes a pulse of sound to travel to distinct points within a 2-meter long tube. This is kind of a short distance, so we need to be able to measure times very accurately since sound moves rather quickly. And we'll do this electronically. I thought I'd just go over here the apparatus that we're going to use. The apparatus consists of the following. So let's start at the sound tube. In the sound tube, at one end, we have a speaker. The speaker produces a pulse of sound. Then within the tube, we have a microphone to pick up the sound. The microphone is movable. It can be moved to any point within the tube. So we can set the distance between the speaker and the microphone and then measure the time for the sound to reach the microphone. That's what we're going to do. How do we create the sound? How do we create the signal that will produce the sound wave at the speaker? Well, we start with a function generator that's going to provide a periodic electrical signal. And in our case, the electrical signal will be a square wave. It will look like this, okay? And what's interesting is that whenever the square wave switches from low to high, that will produce a pulse of sound at the speaker. The reason is that inside of the speaker, there is an electromagnet that's attached to the cone of the speaker. And when the voltage goes from low to high, the current through the electromagnet will suddenly change. And that will cause the electromagnet to move inside of the speaker. And that will produce a pulse of sound, much like striking a drum. So a pulse of sound will be produced here, and then a pulse of sound would be produced here at the opposite point, and here, and so on. We'll set the frequency of the square wave to be very low, maybe 1 cycle per second, so that we only generate 1 or 2 pulses per second, so we can keep them straight. Now, the function generator itself is not capable of driving the speaker very effectively. That's because the function generator is a relatively high impedance source. It can't provide much current. But the speaker is a low impedance load. It wants a lot of current. So in between the function generator and the speaker, we're going to put an audio amplifier, okay? Just as you'd put one between a, do you have record players anymore? Between a record player and a speaker in a stereo system. Okay. How do we detect the sound? Well, we're going to detect the sound with a microphone, and then we'll measure the voltage versus time from the microphone. The microphone voltage tracks the sound. It actually tracks fluctuations in pressure inside of the tube. And the electronics for that looks like this. First of all, the microphone is also a very high impedance source. That is, it doesn't provide much current. So we need to amplify the signal so that it can be measured with an ordinary piece of electronics like this, analog to digital converter. So we have a microphone followed by a microphone amplifier, and then the signal from the microphone amplifier goes to an analog to digital converter, which essentially measures the voltage at each moment in time and produces a number corresponding to that voltage at each moment in time. So the analog to digital converter can be controlled, and we'll set the number of samples per second and also the total number of samples that we acquire. So we might, for example, acquire 1,000 points at 20,000 points per second, okay? Finally, after the analog to digital converter takes its measurement, it will transfer its data to the computer, and then we have a program that will display the data on the screen for us to see. Okay? All of this essentially is using our computer and analog to digital converter as a oscilloscope, a digital oscilloscope, okay? Which just shows us graphs of voltage versus time. Anyway, that's the apparatus.